Hello. Good morning, everyone. It's a great honor for me to be invited here, and I appreciate Professor Yao's invitation, and also appreciate Professor Ho actually created this possibility for this gathering. So now I would like to present something from application point of view. It's research opportunities arising from control and optimization of smart buildings. So first of all, I would like to briefly introduce our center. It's a Center for Intelligent and Networked System. Basically, it was established in 2001 by Professor Ho in Qianchuan University after he retired from teaching from Harvard University. So so here you can see familiar faces, and Professor Shi is part of this group actually. And we also have Professor Qianchuan as our director, founding director, and Professor Ho is our chief scientist. So we have about 30 graduate students as a team, and also our vision and purpose is trying to do intelligent analysis, design, and operation for complex and networked system, which building, of course, is one of the application area. We also include the logistics, supply chain, communication network, and so on and so forth. Now, if you look at my title, you are asking yourself, what do you mean by smart? So now our building is already smart or it's not smart? So I think the meaning of smart or intelligent somehow depending on the context. So depending on where you are from the technology point of view. So here let's look at some advances after 2001. Actually, I think the establishment of CFINS, especially the name, Intelligent and Networked System, basically the kind of in advance of current very hot rising of the ICT, IoT, and also the very hot research recently on AI. So I think, for example, there is a Nature publication saying the Moore's law followed kind of very closely over a very long period of time, about 40 years, and we hope it can continue to grow. So this actually provides the hardware and the software computability to support the things to be more smart. And also, you are very familiar with this because maybe 2 years ago or 1 year ago, so the computer game playing is by Google DeepMind beat the world champion. So it's a very exciting progress. So now I think to be more specific, what I mean is actually we utilize all the information relevant to the whole building systems thanks to the Internet of Things technology as a result of a very fast drop in the cost of hardware, computing, communication, and the storage of data. And also we are able to care about individual occupants thanks to the rapid development of machine learning technologies. So there are a lot of advances from the computer science point of view. But what we can do from the system engineering point of view? So that is a question. Optimization, modeling is a part of our job. We want to kind of catch the capability and explore further. So back to the building itself. So one of the important topics is energy consumption and energy saving. So there are a lot of potential, as it is estimated there are about at least 20 to 30% if you can operate the thing based on your information, which is for free. Now you can, as long as you can use the information properly, then you can achieve this amount of saving. So that is basically from the integration point of view, you can use more information now without kind of too much cost. So So the information is there, is free. But the question is how you utilize it. Now this is a general framework of doing integrated building control for energy saving purpose. And here is a layout of our research platform established 8 years ago in a low energy demo building in Qianchuan University, which Stephens is part of the team, and we collaborate with the building people and public safety people to jointly work on the kind of information fusion and personalized localization and other sensor network, and trying to improve the control efficiency. So the general picture of the energy saving for building system is kind of a closed loop system. You can see a lot of energy format and a lot of control devices, and we also have the human in the loop. We have the human's response, and so to minimize the total energy cost, you have to take the modeling and the interaction among them. So the possible challenges then will be from, I think, two sides. One is the curse of dimensionality and time-consuming evaluation for the purpose of integrated control for building energy purpose. And the other is the machine learning challenge, because the machine learning in general is also a hard question. And the multivariable decision problems all put both machine learning modeling part and also the optimization part. So what are the ways we can address these challenges? I think due to the no free lunch theorem, which was brought to my realization, is from Professor Ho, and we early collaborate with intuitive explanation of no free lunch theorem effort. We published a journal paper, and that indicate even use quantum computing, you cannot actually speed too much up for the search problem in general. So it's we have to do some domain-specific study to make the problem attractable because of dimensionality. So one way to do it is software optimization for integrated control. So a lot of tools invented, including Professor Ho's ordinal optimization as a goal softening, and guarantee going to the probability guarantee instead of best for sure. And also OCBA, we know it, and nested partition, adaptive dynamic programming, or approximate dynamic programming, or Professor Cao's event-based optimization, and IPA, of course, it's all based on some give up some global, for sure, guarantee for a very huge optimization problem. So here I want to mention briefly only one point, and the other is apply the problem-specific knowledge to reduce search space for design good learning algorithm. So the constraint optimization, ordinal optimization idea is trying to solve the feasibility constraint. So for the basic framework, actually, we want to some good enough solution here, and we can sample with a whole space, and here we put some selected set, but here the dots are the infeasible solutions. So the idea is trying to relax all the select set being feasible for sure. We give up a little bit. Then we can achieve a speed up of solving the ordinal optimization problem with some complicated constraints. So this has been applied, this method applied by others in the commitment control with security constraint by power people. So below I will use only a very simple example of modeling the comfort model as a demonstration of how challenges and what we can do with modeling, use some domain specific knowledge. Okay. So here, talking about the HVAC and the thermostators, and people usually don't know clearly what they want when they set up the thermostators, because you can see the statistics. Actually, the set point is kind of random and not very stable, and not too many people know how to set it correctly according to their own demand. Here is a traditional one, and even in this room, and some fancy one, but they all not care about your personal requirement. We introduce human perception and the indoor environment, some personalized learning framework, so that we base our learning from some previous knowledge, which is a standard model. It's called the PMV model. Okay. So the challenge is the existing work is only the average comfort model for everyone. It's just adopted by the HVAC producers, but they don't personalize your comfort requirement. So we set up this closed loop learning model. Here is the occupant interact with our system. We use machine learning to create the model. It's a personalized model, and then we use it as an optimization. We save the energy at the same time maintain your comfort requirement. So here is the first generation one, which you need to use this panel to tell the system whether you feel cold or hot, it's too hot or too cold every 1 hour. We learn the model. Here is some details, but you see the formula is a nonlinear one, and it is a discretized value. It's basically a original value, and we convert it to a nonlinear parameter fitting problem, and use this one to compensate the learning, use the least square recursion, introduce some forgetting factors, we get the result. Here is the layout of the experiment, here is the result. This is the result, and so the insight we get here is that we find really for different individuals, they are different, they have different capacity in energy saving. For example, some people prefer hotter, higher temperature in the summer, which means they are green people. They don't demand very high cooling load. Okay, that's fine. But some people, they prefer cooler than average. But then you have to remind them, okay, if you want to set up your thermostators below the average, then you have to kind of pay higher bill. Then would you like to kind of a little bit adapt to the warmer environment? Then that is a trade-off. Then it is kind of negotiate with yourself whether you want to pay more bill or you prefer to be less comfort, that kind of things. Okay. So, but this still have a limitation very obviously, because every 1 hour you have to tell the system. That is very tedious work. So can we be more friendly? Yes, we introduce this kind of panel, which you just complain. It's too hot, too cold, and if you feel it's okay, then you don't tell the thing to the system. You just leave it. It's an event trigger things. Okay. So use this one, but still you have to build the model. Then the learning input is very limited because you only tell them, I feel cold, but it's very cold or just a little bit cold. That doesn't tell you anything. And there is no comfort samples. Even the people don't touch the too hot complaint, but it doesn't mean he feel comfort. Maybe he's busy doing his work. So this kind of things is a challenge, and we formulate the problem as a learning problem, but the learning problem is actually only has negative samples. It's a one-class learning problem. You don't have the positive sample, which means you feel comfort. You never tell the system. Okay. So how to do that? Here we need some information from the field. We based on the previous PMV model and identify some very critical structure. There are some unidirectional parameters in human perception. It's here the temperature, here the relative humidity, and based on that, we introduce a new learning model. Is a Pareto frontier-based model. Here, this learning model is called multilinear one-class classifier learning. We evaluate our model based on the closed-loop experiment. So here is generally how the model looks like. yeah, you have the red dots only the hot complaints. The cold, the blue dot is the cold complaint. So here is a comparison with the kind of statistical model. Here is the one used to design the HVAC and used for the operation guide for the public building. Okay, but here is a personalized learning model, which you can compare. Then you find some deviation. Okay, quite different. So here is a learning effect. Our model is much better than the other learning method, because other methods you have to guess when you have the positive kind of samples, but which you never get it, you just estimate, but that will introduce a lot of noise. Okay, here we do some closed loop experiment. Here we let the occupant go into the room and stay for half an hour and then interact with the system. We repeat for the 12 days, and here is the result. Here, this is a subjective evaluation after using this closed loop learning method, and you can see here the highest score is 7, but after maybe 1 week or so, we have the about 6 score to give the system by everyone. So it's on average, it's a very good model learned, validated by the field experiment. Here is the number of complaints after the whole days. And here is the false positive rate and false negative rate for the individuals. So we extended this idea to the group of people. And here is a very interesting observation. If we put a large group in a test bed, we see that here is a PMV model is compared with our group model learned from here. We see for group people, you have a potential conflict among peoples. But you still have some commonly acceptable regions here. Then you have to use this model to find out this. Okay, because the thermal comfort depends not only on temperature, but also on humidity. So if you have some dehumidifier or humidifier, then you can control the comfort zone for a group of people. Oh, sorry. So here, I would like to summarize for the building. I use only one very specific example to show that even we have more information, we have more computer power, we still need some human to build the model and try to figure out how to correctly do the comfort control. Without sacrifice the comfort, we reduce energy consumption. So some open problems is accurate occupant counting or localization. Even though for human beings, it's easy to figure out how many people in this area. But for the computer system or sensor network, to correctly estimate how many people in the meeting room or in each area is still a challenge problem. It's because of noise, accumulated noise, especially accumulated error. So it's if you are graduate students, maybe you are interested in develop some kind of deep learning-based method to get a very accurate of number of people in the building. Why that is important? Because, as we know, now the smart building, by smart, it has to respond to the dynamics of people coming in and coming out. And that heavily influences the total load, heating load of the system. So it makes sense, okay? And the other problem is data mining for integrated building control and optimization. By data mining means you're looking at the unstructured data, different format, and maybe some kind of heterogeneous sources of the information, how you can put together the information. And it's not an easy problem, and data mining is also part of the machine learning effort. So again, you cannot just throw all the data into some black box and give you the good learning result. So system engineering people, I think, has a good opportunity to find different kind of challenging problem. As you look back, the building of the comfort model is an optimization problem, basically. Just a better fit and better guess where you feel comfort. Okay. Oh, sorry. So we also have some technical committee, which if you are interested in the research of smart building, you can go there and send us email to join our committee, and we can exchange further. We also have some IFAC smart city, which led by Professor Qianchuan. Is this a part of the effort you joined? No?
It's not led by me, but
Oh, but you are the member?
nice effort.
Okay, so I also wrote some survey paper, and if you are interested, you can go there. Okay, thank you for your attention, and best wishes to Professor Hall.
Thank you very much. We have time for a couple of questions.
Your center is called C-Fins. I always wonder, the F stands for what?
Center for.
Oh, center for.
Because you cannot just since kind of guilty. Okay. Professor Hall may have better explanation.
No,
Okay.
So, David, this app is similar to Informs.
Oh,
Informs.
internet
Okay.
forum.
I always thought there's some kind of financial connection.
Financial. Okay.
Actually, it could be future.
Oh, okay. Center
Also, yeah, first I thought it's
for future. Okay, let's always go ahead of time.
Any others?
I have another question. When you talk about the smart buildings,
Yeah.
the kind of data like monitoring people's movement, occupancy, etc., is easy to get.
Yeah.
But how can you get things like people's preference, whether I like a cooler room
Oh,
or
yeah.
whether I like a hotter room, that kind of thing.
Oh yeah, that in the experiment we actually implement in an app. So the people in the experiment, they just install a small app, and the app can talk with the system, and they just tell the system, I feel too hot today. And our system, after several iterations, about 10 samples of uncomfortable complaints, either too cold or too hot, we try to put together a regression model, multilinear model, which can find the boundary of between the cold and the hot region. Then in the middle, you're likely to prefer to stay there. But the challenge again for the experiment is that I omitted the beginning stage of study. We actually want to do some kind of orthogonal test, which is very formal, and we try different combination of humid and temperature, and let the subject stay in different situations, and then we have the big whole overall picture of how people comfort zone looks like. But it turns out it's very difficult to do that because, first of all, it's time consuming. Most importantly, actually, the subject feel offended if you put extreme condition for them, extremely hot, extremely humid. They will think your system is going wrong, so they will not collaborate with you. They just quit the experiment. So what we did, then later on, we use a closed loop learning. We start from the best guess from the average model. Then maybe it a little bit deviate from the personal comfort preference, and we adjust our guess along with the whole experiment period. And then the people feel it's a little bit uncomfortable. It's about kind of you adjust. Then this guy feel comfort. So what we learned actually is the boundary of the model. It's not just the whole region, because within the middle of the cold or hot complaints, that the people cannot stay for a very long time. So sometimes they will feel your system is stupid and I will quit. So what we collected actually the partial information, but we make the most useful guess for the comfort model. Okay.
Yes, please.
Yeah, I'm going to ask this question. I hope you don't take it as a criticism. But from a viewpoint of a beginning PhD student coming to CFA or something, want to know, is this smart building a hot topic for me to pursue, where I get very good
Okay, so thank you, Professor Ho's advices. So I think I still have much room to improve the presentation. And to answer the very important question for the students, I think the smart building area is getting hotter and hotter in recent days. And our research, this project is supported 8 years ago by an industry partner which investigate $8 million to our university for 3 departments. And now our Chinese government support $30 million, 30 million RMB, a big project to promote the research on smart building. So I appreciate the opportunity that Professor Ho started this chair professor group on our center, and we have the opportunity to do some problem-driven research. This is one of the example, and we have the PhD graduate have finished this research work hired by the real estate. I mean, the 房地产这个 company, they are trying to adopt the technology and trying to even push it further. Okay.
Yes.
There are some interesting, much more fundamental issues that are related to so-called demand response, controlling the demand side as opposed to supply side, which is equilibrium. And this may go back also to David's question. What you have not done yet, to the best I understand, you haven't included the economic mechanism by which, for example, if I'm sitting here and I don't like it and I want the temperature to go up or down, you can create an economic mechanism by which
the business
you can
model.
control my demand. So, for example, I can get some money back from being a little bit uncomfortable if it's better for the local grid state. That's the whole idea of demand response, controlling the demand side. And I think that is an aspect which actually from a mathematical standpoint ends up with some interesting market decision processes.
I didn't include this part, but we have done some work on this. And first of all, from this study, we realized that actually the modeling of people, psychology or their behavior is quite different from the kind of modeling machine or physical process. So that is why we consider the human psychology when we design this learning method. In terms of energy saving business model, actually we did some test with our interface. We just predict the people prefer a cooler environment, and we suggest possible of energy cost for this guy, and we let them decide whether you want to go cooler or just stay because the bill will arise. And if we ask the students, they don't care. They just go ahead and make it cooler because they don't pay the bill. And exactly, if you want to implement the potential of energy saving by learning, you have to create some correct business model and make this sustainable and really for the occupants to adapt this technology. So,
Connected to the grid.
Connect to the grid.
The grid is going to provide the incentive. They're going to say, we don't have enough energy right now. If you building occupants are able to reduce HVAC or AC by 5%
Yeah.
next hour,
Yeah.
get some reward, that gets spread out over the occupants who are willing to participate. There's some really interesting models to be explored there.
Sure.
The human element is important, but
It's depending on how you design the game sometimes.
and those are good PhD.
I mean, I just take a very pragmatic viewpoint. People willing to give you money. That's one evidence that this is a good for your thing. The second is, after so many years, you've got to have
Deliver some product.
tell people, okay, this is what I did. I received this award. People are actually using it. That's the other evidence you need to for this field to keep on being hard and being useful.
Yes.
Support students.
Yes.
Okay, it's about time. So
thank you.
thank the speaker for one more time.